And is the screen visible? Okay. This is the live session for week 4 discussion for fabrication techniques for MEMS-based sensors from the clinical perspective. I am Rayan Jisma. I'm your course TA. This week uh, we'll have the discussion on whatever topics that were covered in week 4. Okay. So about me, this is about me, and every week on Monday from 6 to 8, I'll be having the live session. This is the meeting link, and these are the places where the files will be uploaded. If you have any doubts, you can reach me at the following email. Okay. In week 4, the topics that were covered were fabrication of VOC sensor, fabrication of VOC cantilever, and chemical vapor deposition. So these are the 3 topics that are covered. We can start with the problem session. So I hope that this problem session will be more interactive. Okay. 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 First, we'll start with problem number 1. We can improve the sensitivity of the sensor by using nanostructure of a metal oxide than using normal metal oxides. Is the statement true or false? So what do you think the answer is? You can guess the answer. Should I repeat the question again? No, you can guess. It's fine if the answer is wrong. It's fine. Okay. Okay. Uh, okay. You would have seen that there are certain sensors, especially where they have they use metal oxides in order to sense whether any material is present, like any material or gas is present or not. So what happens is that these metal oxides will react with the gas and they will form some sort of compound. By sensing the properties of those compounds, you can detect whether, like, how much gas is present or what kind of gas is present. So here in this problem 1, what is asked is that instead of using a normal metal oxide, what happens when we are using a nanostructure of a metal oxide? Does it improve the sensitivity or not? Okay. Like generally, what do you call as nano material? What do you think a nanomaterial is? Yes. So one of the dimensions should be in the nanometer range. Then let's say as we are reducing the size of something, what happens to the surface to volume ratio? Surface to volume ratio, yeah, the surface area divided by volume. It increases, right? As we have more surface compared to the volume, what happens is we'll have more area for the any component that we want to detect to react. So what happens is the sensitivity will also improve. Uh, so we can improve the sensitivity of the sensor by using nanostructure of a metal oxide than using normal metal oxides. The statement is true. So the answer is true. So next we'll move on to problem 2. Which of the following parameters do not affect the deposition rate of CVD process? So CVD is chemical vapor deposition. It is a type of deposition process. So the options are A, precursors and their partial pressure, B, length of the susceptor, C, activation energy of the precursors, D, rate of carrier gas flow. So yes, I'll just explain what chemical vapor deposition is. So in chemical vapor deposition, what we actually do is we will pass two kind of precursors in two or even one precursor in the gas phase by reacting different gases at like desired conditions. We will deposit the material on the surface of the substrate. So it is deposition due to chemical reaction between the vapors. But the deposition happens on the substrate. So that is what is chemical vapor deposition. So here, yeah, in these options, you can just try to guess what it is. Which of the following parameters do not affect the deposition rate of CVD process? You can just guess. What do you think the answer is? No, wait, here it is as okay. You're thinking it is rate of carrier gas flow, right? Okay, it's fine. So here it is asked which of the following does not affect. Okay, so here you can see just a like basic diagram of how the CVD happens. So we have some gases called precursor gases which will react. So generally we'll have a tube. This tube will be quartz tube where we will flow gases. So at one side of the tube we'll have an inlet and at the other side we'll have an outlet. Then we will have some, this is called susceptor, where we will place our wafer. So we can either place it like this or in a horizontal fashion like this. So this is called a susceptor. And we'll have an inlet and outlet for flowing the gases. So what happens is, first we will introduce the precursor gases. Then we have to transport those species to the substrate. Once that has happened, uh, the reactive species will get adsorbed on the surface of the substrate. Then, if there are two or more reactive species, some kind of reaction will happen, and film formation will also happen. Then, after this, there will be desorption of reaction products. Then, this reaction product will get transported to the flow where like general flow in the chamber, and then we will have the removal of the reaction products. So this is the basic uh, mechanism by which the CVD reaction happens. So now here like I'll just give a clue. So here precursors and partial pressure means it's the gas length of the susceptor is length of this activation energy of the precursor is like for the reaction to happen there is certain amount of energy that you have to supply, otherwise the reaction will not happen. So you can consider that as the activation energy of the precursor, rate of the carrier gas flow. Now can you try to guess again which do not affect the deposition rate of CVD process? You have any answer, different answer? Uh, uh, okay. So the correct answer is length of the susceptor. I'll just tell you why. Sorry. So here you are flowing. Uh, One thing is, like in the CVD, you can actually control the pressure of the gas. You can also control the temperature in general. You can make sure that the pressure is somewhat uniform so that it will like for a particular length, you can have the proper deposition. So the length of the susceptor will not be a main factor. Uh, so first option is what? Precursors under partial pressure. So that is very important. Yes, because that will decide you like it will uh, how much gas is reacting, not how much is reacting. So like partial pressure is actually the pressure that is exerted by individual gas within a mixture of gases. So you can say that if you are having a reaction or a growth rate, that will be proportional to the partial pressure of the gases. Then the activation energy of the precursor. So here, like what is happening is it is getting adsorbed. After getting adsorbed, it should react. So generally, for any reaction to happen, like if you just mix two things, the reaction generally does not happen. Only if you have supplied some energy which is greater than the activation energy for the reaction to happen, then only the reaction happens. So activation energy of the precursor is also like it will affect the deposition rate. If you have not supplied enough activation energy, your reaction will not start. But if you have given enough activation energy, your reaction will start. The rate of the carrier gas flow, that is also important. The carrier, so sometimes precursors, we will mix them with carrier gas flow as well. So if you the rate of the carrier gas flow will determine the overall pressure in the chamber as well. So that also will play a role. The length of the susceptor will not play much of a role because it like it is you will just keep it in certain region of the chamber where you can maintain like proper pressure and temperature. Like you will not keep it infinitely long. So that is not going to affect the deposition rate as such. Is this clear? Okay. So next, so the answer is length of the susceptor for this question. The next one is at lower pressure, an increase in mass transfer coefficient during LPCVD process will change the mode of operation. How will the process change? A is the system operation switches to the mass transport limited regime. B is the system operation switches to the surface reaction controlled regime. C, the system operation switches to the diffusion limited regime. None of these. So here LPCVD is low pressure CVD, low pressure chemical vapor deposition. So there are different types of CVD based on like either pressure, what kind of pressure you are operating, you are doing the chemical reaction, and also what kind of energy you are supplying in order to bring about the chemical reaction. Among that, LPCVD is one of them. So here it is mentioned that you are operating it at lower pressure, and in the name also it is low pressure CVD. What is asked is an increase in the mass transfer coefficient will change the mode of operation. How will the process change? So before that, I'll just explain one more thing. Uh, okay. So here you can see that there are two main things, right? One is transport of reactive species to the substrate, and the other one is the reaction at the surface and the film. So let's say I'm having my substrate here. So this is my substrate. this is some gap, and here I am having the flow of the precursor. Mm. So my precursor has to flow from here to the substrate, and then at the substrate it has to react. So here the flow from where flow of the precursor from like where the normally the gas is flowing to the surface of the substrate happens by a process called as diffusion. So this will actually depend on the concentration gradient between the two regions. And since it is happening, this transport is happening by diffusion, you can call this as mass transport limited. So like how much is the how much is getting transported from the gas to the surface of the substrate will tell you how much of the reactants will be present at the substrate. Okay. So once the reactants are transported to the substrate, the reaction has to happen. So for the reaction to happen, it should have some particular reaction rate. Again, this reaction rate will be dependent on temperature. If you are not giving sufficient amount of energy in order for that reaction to happen, then like I told, the reaction will not happen. If you have given sufficient amount of energy, then the reaction will happen without any issue. Uh, so there are two main processes. One is transport of the reactants from the precursor to the substrate surface, and the second one is the reaction that is happening at the surface. One is transport that is happening, and the other is uh, the reaction that is happening at the substrate surface. So this transport is like how much mass is getting transferred from the gas phase to the surface of the substrate. The reaction is how much energy is supplied so that it will get the particular reaction will happen. So here what we are telling is at lower pressure we are increasing the mass transfer coefficient. So we are increasing how much mass we are transporting from the gas phase to the surface of the substrate. So this will change the mode of the operation. How will the process change? So since the CBD reaction depends on two main processes. Let's say if your transport is not happening well, like you are transporting only less number of species across the substrate, then like your how much reaction or how much film you have grown will depend on how much mass you have transported. Is this clear? Similarly, let's say you are transporting as much, there is no limit in the transport. You are transporting more amount of mass towards the surface of the substrate. However, if you're at the surface of your substrate, if you are not providing enough energy, either by temperature or some other mechanism, then your reaction will still not happen. So in that case, you can tell that as reaction limited regime. So that is what is meant by mass transport limited regime and surface reaction controlled regime or diffusion limited regime. So here, what is asked is you are increasing the mass transfer coefficient. Then what will be the limiting factor in this case? If I'm increasing the mass transport, what will limit my how much film is grown? Yes. So what do you think will limit it? Yeah. What do you think will be limited here? You just have to tell whether the which one is getting limited. Is the transport getting limited, mass transport getting limited, or is the reaction rate getting limited? So here, what you are doing is you are yes, because you are providing enough mass, like you are transferring enough amount of reactants uh, to the surface. However, your reaction rate, if you are not supplying enough energy, then your reaction rate will get limited. So since we yes, so the option will be option B. It will switch to surface reaction control regime. It is not one because already here it is mentioned you are increasing the mass transfer coefficient. So it is not limited by mass. And diffusion is same as the mass transfer. Uh, so the option is answer C. B. Okay. So next one is problem 4. Which of the following deposition techniques requires the highest vacuum levels for operation? One is LPCVD. LPCVD is low pressure chemical vapor deposition. MB is molecular beam epitaxy. APCVD is atmospheric pressure chemical vapor deposition. So highest vacuum, not highest pressure, highest vacuum. So which one is the uh, correct answer? So which one do you think is the correct answer? You can like do it by elimination, like at least because since you don't know the exact pressure. So here you need a yeah, yes, option B is correct. Yes. So this is atmospheric pressure, right? So it will be around atmospheric pressure, which is 1 bar, or it may be slightly higher. So this is the pressure at which the APCVD deposition happens. In the case of sputtering, the deposition pressure is generally in 10 millibar to 10 bar minus 3 millibar, like less than a little bit less than 10 bar minus 3 millibar. You can say 10 bar minus 4, around 10 bar minus 4. In the case of LPCVD, it is low pressure. So it happens in somewhat in vacuum, but not in very high vacuum. So this also is between 10 millibar to 10 power minus 3 millibar. In molecular beam epitaxy, where we are doing epitaxial growth, there we need very high pressure, which is 10 power minus 9 millibar to 10 power minus 12 millibar. The answer is molecular beam epitaxy. So in sputtering, we do not require that high, like that high vacuum, and the mechanism requires that like with this kind of vacuum, it is essential for the deposition process. So answer is molecular beam epitaxy. Next, we'll move on to problem 5. Which process is used to produce high purity, high performance solid material? A is chemical vapor deposition. B is sputtering, C is evaporation, and D is electroplating. So which process is used to produce high purity, high performance solid material? High purity is very important. Uh, like among which will produce very high purity. Yes, it is chemical vapor deposition. In the case of sputtering and evaporation, we are doing physical vapor deposition where we already have the solid material. We convert it into vapor, and that also can get converted into vapor and will get deposited in the substrate. So the purity will depend on the purity of the target material that you are using. In the case of electroplating also, you need to have very high purity material. Like there is a chance that something else may also can get deposited. In the case of chemical vapor deposition, you are using two gases in, let's say you are reacting two gases in order to get a particular deposition. You can do distillation of the gases as well in order to purify them. So with this, you can get very high purity and high performance solid material, like especially like semiconducting materials. Okay. So answer is chemical vapor deposition. Mm. It will have some purity, but no, like CVD and electroplating do not like we are not using it to deposit the same material. So here, especially here we are especially talking about semiconducting materials, CVD, not electroplating. Mm. So next is problem 6. Volatile organic compounds are formed from their respective liquids easily because of A. Low diffusivity at room temperature. B. Low vapor pressure at room temperature. C. High vapor pressure at room temperature. D. High sublimation temperature. So VOC, volatile organic compounds are also called as VOC. What do you think the answer is in this case? Yes, high vapor pressure at room temperature. So if you have high vapor pressure, then the compound will have more tendency to remain in vapor state rather than the liquid state. So this is the correct answer. Diffusivity means how well like it can move from one region to another based on the concentration gradient. So that is not an answer for this. And in the case of sublimation, what happens is sublimation means you are converting from solid phase to vapor phase. Right. But that is not what is happening in like since it is mentioned that they are formed from the respective liquids. So vapor pressure, high vapor pressure at room temperature is a correct answer. Um, we'll move on to the next question. Which of the following are different types of CVD? A. Atmospheric pressure CVD. B. Low pressure CVD. C. Plasma enhanced CVD. D. All of the above. Yes, all of the above. So in atmospheric pressure CVD, like I told before, it works at atmospheric pressure. So around 1 bar. Uh, in low pressure CVD, it is around I think 10 millibar to 10 power minus 3 millibar. In plasma enhanced CVD also we'll have similar pressure. So only thing is in these two are the energy for the reaction is applied by means of the temperature. So uh, the substrate or the entire chamber is heated. In the case of atmospheric pressure CVD, only the susceptor will be heated, where we are loading the samples. Only that region is heated selectively. So the reaction will happen only where the samples are present. But in the case of low pressure CVD, the temperature uniformity is very important in the deposition. Since we are doing this deposition at low pressure, the other variable that we can control in CVD is temperature. So we have to ensure that we have uniform temperature for proper deposition. As a result, the entire like quartz tube where the chamber of the CVD will be heated. So there will be uniform temperature throughout the chamber. So here, in the case of atmospheric pressure CVD, the pressure is very high. So the rate of growth of the film is also proportional to pressure. So it can grow very fast, but the quality of growth will not be as good as that of low pressure CVD. Since the pressure is very high, the rate will primarily dependent on pressure and not much on temperature. The chamber is designed in such a way that, like with pressure, there we will be supplying heat, but like the heat will be enough for the reaction to happen, but it will not like if you are increasing the heat 2 times, it will not improve your growth rate. But in the case of low pressure CVD, the temperature has to be maintained uniformly. So the deposition depends on temperature, but we will be able to get better quality film growth, especially for semiconductor films by using low pressure CVD. In plasma enhanced CVD, we are using plasma as an energy source for the reaction to happen. So we can have comparatively lower temperature than that of atmospheric pressure CVD and low pressure CVD for reaction to happen. So that is the main difference between the three. So both all the three are different types of CVD mechanisms. Okay. Next we'll move on to problem 8. Which of the following statement is true for APCVD, which is atmospheric pressure CVD? A is a low sticking coefficient of deposited material gives better step coverage. B is high deposition rate. C, widely used for silicon deposition. D is all of these. And you can have multiple choice as well. This is a multiple choice answer. What is the answer for this? So step coverage means, let's say generally in fabrication process, we will have multiple layers of processes, right? If you are having a step like this, if you are in your you have done some processing, your profile is looking like this. You are having some region which is having which is higher than the other region. So then this is some kind of step, right? You are having a hill and you are having a valley. So step coverage means when you are having when you are depositing a material, it should follow the step. There should, like in the horizontal region, like how much stick you have deposited in this region should also be present in this region. In the side walls as well as in the corners, you will have the same amount of film growth, like same thickness of film. This is called a step coverage. It should follow the exact step, and also like the thickness should be the same everywhere. in the side walls and in the corners also it should be the same. If it is not the same, some cases, like in some deposition steps, like if you are having a step like this, you will get more deposition in this region, and in this region. In the side walls, you will not see any deposition. So this you will call as poor step coverage. And if you are having this, it is a very good step coverage. In some cases, it will be little bit in between also. Like there will be some deposition in the side walls, but not as much as in the steps in the in this and this region. So what do we? Uh, 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 okay. So the option is option D actually. Here, D. So this is correct. Uh, Option A is correct. So if there is low sticking coefficient of deposited material, then it has been seen that it will give better step coverage. Another thing is that in APCVD we are having the deposition at very high pressures, at atmospheric pressure. So the amount of gas flow will also be very high. The growth rate will be proportional to the pressure. So we'll have a very high deposition rate. Yes. So this is also correct. Then in the third one, uh, widely used for silicon deposition. Here, since it is having higher growth rate, it can also be used for depositing silicon. But one thing is, this silicon will be polysilicon. Since there is not enough energy, like not enough temperature given on the substrate for the deposited silicon to be oriented in a proper manner. So, like the orientation or the reorganization of the crystal will not happen. However, we can use it to deposit polysilicon. So the answer is option D, all of these. Is this clear? Okay. Uh, so we'll move on to next question. Uh, Problem 9. Which of the following is true for PCVD systems? A is uses high temperature. B. Damage due to plasma. C. Useful for dielectric coatings. D. Low non-conformality. So you can eliminate, I think, you can, this is multiple answers are correct for this question. So what do you think the answer is? So this is plasma enhanced CVD. We are providing the energy by means of plasma, energy for the reaction by means of plasma. Which is true. It is. Uh, so you have any answers? Uh, so A is wrong because since we are providing the energy for the reaction by using plasma, we can reduce the amount of temperature that is needed for the reaction to happen. So, yes. So generally, the temperature can be around, I think, 200, 300 degree in order to deposit films of SiO2, silicon nitride, and so on. So since it is plasma, there is possibility that there may be damage due to plasma. This is correct. Then it is useful for dielectric coating. So silicon dioxide, silicon nitride, like that can be deposited by using PCVD. So this is also correct. Low conformality, this is wrong. So generally, if your reaction is temperature limited, it has to be self-limited for a film to be conformal. In what does conformality mean is that if you are having a topography like this, if you are having a conformal film, then once you have deposited that film, it should follow the underlying topology like this. So, like once you have deposited the film, you will have that same topology on top. So that is called as conformal film. So, irrespective of not having very high temperature, plasma enhanced CVD seems to have conformal deposition. So the answer is both B and C for problem 9. Okay. So next, we'll move on to problem 10. In low temperature regime of CVD, rate of reaction, uh, option A does not vary significantly with temperature. B is very sensitive to temperature. C is very sensitive to molecular weight of precursors. D, at the surface of the substrate, does not depend on crystal orientation. So I think in one of the earlier questions I already told that there are two main mechanisms which is happening. One is transport of the precursor, and the other is the reaction at the surface of the substrate. So here, this is like how much mass is transported from the gas to the surface of the substrate. In the reaction, how much temperature is present so that the particular reaction can happen. So, like with this explanation, I think you can tell if you are having low temperature, it will be very sensitive to temperature. Yes. So, option A is wrong. Uh, then option C is also wrong because here that since the temperature is low, that temperature becomes a limiting factor. Uh, then option D is at the surface of the substrate, it does not depend on crystal orientation. So if you are trying to grow any oriented film, then like the growth will happen at somewhat higher temperature, not at lower temperature. Like using LPCVD, if sufficient high temperature is provided, then the film growth will have the same orientation as that of the substrate, but the rate of reaction does not have any like direct dependence on the crystal orientation because the reaction is dependent on the precursor, right? The precursors are the one that is reacting. So the even the activation energy will be for the precursor, not for the substrate. Okay. So the answer is option B. Is very sensitive to temperature. Okay. We'll move on to next problem. Problem 11. A silicon wafer is doped by diffusion of boron to a depth of 200 nanometer to define the active device area. Next process requires deposition of a silicon dioxide layer as an insulating layer. Which deposition technique can be used so that the deposition profile will remain unaltered? So let's say you are having a silicon wafer and you have uh, for a depth of 200 nanometer, you have done you have doped the silicon by diffusing it with boron. Next process requires deposition of silicon dioxide as an insulating layer on the top. So you need to deposit SiO2 on top. Which deposition technique can be used so that the deposition profile will remain unaffected. So if your temperature increases, then your uh, whatever diffusion you have done, it may start to spread out. It will not remain in this 200 nanometer region. So you have to have a very like uh, strict control on temperature. Okay. So with this, can you tell which? Ah, yes, low pressure CVD, because that is the one that will have no, it's not low pressure CVD. Low pressure CVD, you need to have uniform temperature, so the temperature will be high. If your temperature is very high, then there will be more diffusion of the boron. It can diffuse in deeper, so your doping profile will change. Uh, this means you cannot go beyond a particular temperature. You have to maintain as low temperature as possible. Plasma enhanced is an answer. Yes. We'll use less temperature. So not this one. Answer is plasma enhanced CVD. So generally, when you are having you are doing processes, no, they'll do this thermal budgeting where different materials that you deposit or when you do doping, there is only a certain within a certain temperature range it will be stable or it will be fine. If you go beyond a particular temperature range, then the whatever, if you have doped, no, that it may diffuse in further. Then like if you are having some certain materials, if you are going close to the melting point, then the material will start to melt. So because of that, you cannot go to there'll be a certain range of temperature within which your process should like your process steps should be. So depending on that, we can actually choose different uh, type of deposition processes. Like if our thermal budget is low, means we cannot go to very high temperature, then we have to choose a process which will do the deposition at lower temperatures and so on. Then next is problem 12. A person needs to grow or deposit 111 oriented silicon epitaxially. His options for his growth are APCVD, B PCVD, C LPCVD, D evaporation. 111 oriented silicon epitaxially. What? Okay. So it is not evaporation. Then here among these three, we have to see which one is the correct one. Okay. So in order to grow epitaxial films or films of very high quality, we need very high temperature. Because that orientation, there should be like sufficient amount of energy that is given for the reorientation to happen. So if you look at the uh, no, APCVD is high pressure. So temperature does not play much of a role in the growth. So it is not APCVD. In PCVD, we are giving using plasma as a energy as one of the source. So we do not generally need very high temperature in that case. Uh, Here we can deposit silicon, but it is amorphous silicon that whatever we can deposit, not crystalline. So the answer is LPCVD. Here, by giving sufficient high temperature, we can deposit 111 oriented silicon epitaxially. So next is problem 13. When depositing silicon dioxide using LPCVD, higher temperatures are needed to achieve non-conformal deposition. Is this true or false? Uh, okay. So this is no, it's not true. It is false. The reason is that for conformality, generally, if you have a any deposition process, if you want conformal deposition, then there should be like the reaction should happen somewhat uniformly in all the regions, right? So let's say in the case of LPCVD, since temperature is involved, you need to have uniform temperature throughout. Like higher temperature will give you a higher deposition rate, but the temperature should be uniform. Like if you are having uniform like high temperature, then you will get conformal deposition. But if the temperature across your wafer is not uniform, in some regions it's higher and some regions it is lower, then you will not get a conformal deposition. So like higher temperature is not required to get a conformal deposition. If you are having non-uniform temperature, then only you will get a conformal deposition, non-conformal. Yes. So like along the wafer, at every surface, it should be the same. The temperature should be the same. And that's why in the case of LPCVD, like they instead of here they will have a susceptor inside a quartz chamber. So instead of just heating the susceptor, they'll heat the entire quartz chamber so that there will be uniformity in the temperature. Okay. Um, is this clear? Okay. We'll move on to the next question. PCVD is useful for deposition when A. Low melting temperature films are present on the wafer. B. Very low deposition rates are required. C. There is no thermal budget available for the doping profile. D. LPCVD is not an option due to contamination restrictions of the available tool. It's multiple choice. So this is okay. This is correct. Yeah. Yes, that is also correct. So any more answers? So, like, since in PCVD we do the deposition at lower temperature, if we are having low melting temperature films, then we can go with PCVD. And also for doping profile, since we don't want to have a higher temperature process, we can go. Another thing is LPCVD is not an option due to contamination restrictions of the available tool. This is also correct. So let's say certain materials like gold can diffuse very fast. So like in LPCVD, since it is a very high temperature process, it is generally like oxidation furnace or so on. So it will have some requirement for cleanliness. Like certain materials will not be allowed. If in your case, like your substrate is having some film which is not allowed in LPCVD, then you can go with PCVD deposition process, which is a low temperature process. Okay, so option D is also correct. The correct options are option A, C, and D. So these three are the correct answers. Is this clear? Okay. So next is problem 15. It is possible for ions to enhance H rates significantly when they act in conjunction with free radicals. So this question is related to dry etching. It is possible for ions to enhance H rate significantly when they act in conjunction with free radicals. So in dry etching, um like there are different types of dry etching. Uh, One in which like we have only the free radicals. In the second one, we only have ions. In the third one, we'll have free radicals plus ions. So what happens is like if you're having free radicals, what it will do is uh, like so in dry etching plasma is required when these free radicals will get adsorbed on the surface of your substrate, let's say silicon, uh, and it will react. Then it will form some byproduct. The byproduct will be generally volatile in nature, means it will evaporate as gas, and like whatever reactants that are formed, that also will be volatile. So free radical is generally chemical based reaction. Uh, these are chemically reactive elements like fluorine, so they will just get adsorbed on the surface of silicon, react with silicon, and the byproducts will get dissolved and they'll be evacuated out. So by this, the etching happens. In the case of ions, what happens is that the plasma will provide sufficient amount of energy to these ions. So these ions will bombard on the substrate. So like what will happen is we'll have physical bombardment of the ions on the substrate. Like since a large amount of energy will be given to these ions, when these ions bombard on the substrate, it will cause some of the atoms from the substrate to be ejected out. So, like by physically bombarding on the substrate, it will remove material from the substrate. So that is like the type of mechanism when only ions are used to etch. In free radicals plus ions, what happens is we'll use a combination of both. We'll have free radicals that will be adsorbed on the surface, but some cases like the whatever reaction products that we are getting may not be volatile in that case, or the reaction rate can be like very slow. In both the cases, we can use ions in order to remove the additional material from the substrate. So the answer for this question is it is true. So by like we have to adjust the energy of the plasma and the concentration of the free radicals, pressure, and so on, so that like we can enhance the H rate significantly. Okay. So the answer is true. Uh, Next is problem 16. At low pressure, an increase in mass coefficient during. Okay, I think this we had this problem earlier again. Earlier. Next, we'll move on to problem 17. Which of the following is true for APCVD system compared to LPCVD system? A. Poor uniformity. B. Simple. C. High throughput. D. High purity. E. High deposition rate. F. Less consumption of gases. Which of the following is true for APCVD system compared to LPCVD? So APCVD is atmospheric pressure CVD. In APCVD, we'll have higher pressure. Right. So the growth is proportional to pressure. It does not depend much on temperature. In the case of LPCVD, we are maintaining the chamber at lower pressure. So the growth is mainly dependent on the temperature. So for APCVD system, which of the following is true? It's a multiple choice answer. Multiple answers are correct. Yes, high throughput is correct. Yes, that is also correct. So any other answers other than these two? Huh. So it also has like there is chance for poor uh, uniformity. Why? Because like it is dependent on pressure variation in chamber, right? So let's say you are having your samples here. Here you are passing gases, and here you are removing them. So here you will have more amount of reactants. Here you will have less amount of reactants. So the uniformity, like there is chance for poor uniformity as well. The system is very simple. Why? Because we do not need it to maintain at very high vacuum. So we don't need very complicated vacuum pumps. We need just a simple vacuum pump that could uh, like uh, if you want to go little bit lower than atmospheric pressure, then just a very simple vacuum pump is enough. So the system is simple. In APCVD, generally, since we have a higher deposition rate, we go for high rate deposition, like deposition of thicker materials in faster. So purity wise, if you compare to LPCVD will have a better purity compared to APCVD and less consumption of gases. So in atmospheric pressure CVD, will flow more amount of precursors in order to bring about the reaction. So we are consuming more gases. So these two are wrong. So the correct answer is poor uniformity, simple, high throughput, and high deposition rate. So these are the correct answers. So this is when we are comparing it with LPCVD. Yeah. Then one more question regarding the deposition process, not deposition, like the fabrication steps. Since yeah. In the recap, we had two fabrication of VOC sensor and fabrication of VOC cantilever, right? So I'll ask one question regarding that as well. So let's say I'll draw a cross section of a cantilever. So silicon. Okay. This is gold. This is polysilicon. So what do you think are the steps that will be required to fabricate this kind of cantilever structure? Is my question clear? Uh, so I'll start explaining. Uh, or you have like you can tell the answer. So first is we'll take a silicon substrate. Here you can see that there is some amount of like gold deposited, possibly as bottom electrode, right? So and also you can see that it is not deposited everywhere, only in certain small regions. So first we'll have to do uh, lithography, where we use we coat photoresist, then we expose photoresist only in some regions. So if you are using either positive or negative photoresist, after exposure, photoresist is present only in the regions where you want to protect, and it is not present in the region where you want to deposit. Then you can go for metal deposition process. So after this, you can deposit metal throughout. So if you are depositing by evaporation, then it is like non-conformal. So it will deposit, and it is line of sight. So it will deposit only in the regions. Like it will not deposit on the side wall. So you will not see any side wall coverage as such. So after this, you'll go for lift off, where you will put the entire substrate in solvent. So what happens is once you are doing lift off, the like metal that is deposited on the PR will go, and the metal that is on the substrate will remain. So after lift off, what happens is that the metal will be present only in the regions where there is where there was no PR. So then after this, you need to have a cantilever on top. So there is also some gap between the bottom electrode and the cantilever. So you'll follow this by depositing some sacrificial material on top of this. Okay. So here you have silicon. Uh, on top of this, you will have already gold electrode. Then you'll deposit some sacrificial material on top. So this sacrificial material can be anything, like it can be SiO2, silicon dioxide, silicon nitride and so on. So only thing is it should get easily etched. So after this, you want to have some region where you can anchor your cantilever, right? So you will have to pattern this sacrificial material again. So after this, what you'll do is you'll again do direct writing and lithography, direct writing or mask writing, any type of lithography. Uh, Here you will be having your gold metal, and then this is your sacrificial layer. So here your photoresist again will protect the regions. It will be present in regions where you want to protect, and the region where you want to etch will be exposed. So after this, we will do the etching process where we will remove this material. So after etching, what we will have is silicon, then the gold electrode, the sacrificial material will be etched like below the like regions where there was no PR. So remaining regions, sacrificial material will be still there. Next, we'll go for polysilicon deposition. The polysilicon will get deposited everywhere. And if we deposit, oh yeah, if this step height is like sufficiently large, then we can ensure that it is completely covering. Then we'll have to etch the polysilicon layer. For this also, we'll again do one more direct writing. So this is polysilicon. Blue color is polysilicon. In order to etch polysilicon, what we'll do is we need to protect this much region with PR. And so we need this kind of shape for the cantilever, right? So we can protect this much, and the other region we can etch. So after etching, what happens is, uh, after etching, this region will remain, and so your sacrificial layer also will remain. So once this is done, you just have to remove the sacrificial layer, and then you will have the cantilever structure. This is polysilicon, and this is gold. Is this clear? These are various steps in the surface micro machining process, and I think some of them you would be seeing in the cantilever. Yes, if it is a polysilicon cantilever, you will see the same steps. So that's all for this week. Any doubts?